and welcome to Cooking with Dr. T. All right, I'm just kidding. But we want to talk today about pulleys, and I want to use some water and a scale that I could find in my kitchen, so here we are. So I was hoping to do an experiment that you could do at home, and I thought, well, what if I got two water bottles? And one of them has water in it, one is empty, and I thought, well, I'll just take a shoestring, something everybody has, and try to balance these around a rod. And well, it doesn't really work, right? Because it's so unbalanced. But interestingly enough, if I just put some water in my second water bottle here, now you can tell there's huge differences in the amount of water. But if I pick this system up, and again, I just have a screwdriver here as something to slide them on. Oops, I'm all the way to the end. Whoa, there we go. Now it started to slide when it no longer had that back friction. So I get some sliding, maybe not as much as you might have expected, and I can add a little more water, maybe about half. And if we try that again, they kind of don't really move. And so we want to think about what's happening in this system, because the idea that we want to introduce is actually pulleys. And pulleys, let's just switch this to a pulley system. I'm going to take this off the lid here and slide it through my pulley. Hold on a sec, we'll be right back. All right, so we're back, and I've thread the shoelace through our pulley, and as I pick these up, whoa, that didn't take long at all for the water bottles to slide. But when we had them on just the screwdriver, we didn't really see any sliding, even though they're about half the difference in weight, or at least half the difference in how much water is in them, which would lead to about half the difference in weight. But they very quickly slide. And so we want to point out that it's important that we realize that pulleys are frictionless, and that even this tiny screwdriver, because I wanted to suggest you try this at home, and with a rod if you could find, even this water bottle, putting your shoestring around the neck here, but you get so much friction that you don't really get an opportunity to understand how pulleys work. Now I'm going to fill both bottles until they're the same amount, and I've already pre-measured this, and so they got the same amount of water in them. And now when I use my pulley, I get no movement. And the interesting thing is that I could actually start the movement. As soon as I let go, it still stays static. So I can manipulate the system, but as soon as I let go, because of the equal weights, those stay static. And what we want to get out of looking at this, obviously those two have the same weight, but what does that mean about the tension on either side of the cord? Okay, and this is the key principle in pulleys, that we're going to see the same tension on both sides of the cord. So let's do another experiment so we can actually prove this to ourselves. All right, we're back and we're ready for the second part of the experiment. So I've gotten rid of the shoelace, and now I have just little strings attached that have loops on them, so I can at least pick up my equally weighted bottles. And now I have some scales, and these are digital scales. It'll make it easier to read, but with hooks on it, and both of them are going to be attached to a water bottle, and the pulley is in between those. Now the weight's going to get a little heavy, and so I have an additional spring scale. This one is not digital, that I'll actually use to pick up the whole system. All right, so now we have our system set up, and I'm going to go ahead and pull. And so if we zoom in, we should be able to see our scale readings. And just for fun, we're going to also zoom in and see what the reading is on our upper scale as well. All right, now when we zoomed in and looked at our slightly less than precise spring scale, we saw that it read a little bit over 5, like around 5.5. And that's a little odd because both of our water bottles were reading at about 2.3, about 2.28 pounds. And so if we were to add that up together, we're at about 4.5 pounds of water weight. So how are we getting an additional pound to get that almost 5.5 pound reading off of our spring scale? Well, it turns out that you often might need to include the mass of the pulley, because our pulley was hanging off of our spring scale, so we had that weight, and we also have the weight of our 2 digital scales. And if I were to go ahead and use this scale here and weigh them, balance them all on there so we get all the weight, we see that it's actually just over a pound. And so that would explain why our larger spring scale gets a 5.5 pound reading instead of the 4.5-ish that we would expect from our 2 water bottles. So from that experiment, hopefully you saw that the weight on either side, or the tension that's going to be in our cord, string, cable that's around our pulley, is the same on both sides. But let's go to the board now and make sure that we can draw a free body diagram that and understand the statics. So we made it to the board, and we just want to quickly draw what we saw. So we had our pulley that we could say is right there, and going around the pulley we had the string, but we know that we also were pulling up, right, on our pulley with the spring scale. So we can actually now draw on here some of the different forces that we're going to have acting. So we'll draw the forces that are going to be in our cord, which is our cable that goes around our pulley. We're going to have the force of the pulley coming up, and then we also noted that for sure the pulley had some of its own weight. Depending on what the loads are, we include or don't include that mass. In each problem you'll be told whether or not to include the mass of the pulley. But we would have our force 1, we're going to have tension 1, tension 2 in those cables, and then we'd also have the mass times gravity. And so the real question that we're concerned about is the relationship between T1 and T2. And I think you've already figured it out now based on our experimentation and what we saw, but we see that T1 always equals T2, and that's really important. So we can say T1 equals T2, just equals T if we wanted to. And in fact, for this system, which is similar to what we had, I've taken out the mass of the gauges that were hanging off of, or the digital scales that were hanging off the cord, because you normally wouldn't have those there, but you definitely could potentially have the mass of the pulley if it's not negligible as compared to your loads. So if we wanted to sum forces in the Y, we could basically say that we'd have an F1 going up, we'd have minus 2T, I've got a T on each side, and we said they could all be equal to T, and minus mg. And so very much like what we saw in our spring gauge, right, our spring scale, we could see that F1 has to equal to whatever in T1 and T2, or the 2 T's, and the mass of the pulley. And so that's a basic primer of how pulleys work. But if you can remember this key and critical relationship, this is the most important thing. If you can remember that, pulleys will be a lot easier.